Kerbal Space Program is a lot of fun. The simulator that we're starting with for the first homework is a sort of more boring simulator called Gazebo. This is Gazebo, and it allows the simulation of actually a wide variety of sort of research robots. That's what it's for, is doing physical simulations in some detail of robots that are useful in research. So what we have here is the simulation environment for homework 1. We have this big gray plane, and on the big gray plane we have some chunks of brick wall. We have some, looks like fire hydrants, a whole bunch of fire hydrants. We have a little bit of texture on the ground. The goal in homework 1 is going to be to write a control program that drives your robot to this checkerboard texture. That's the goal. That's at a fixed known coordinate in space, and for homework 1 you're going to get a position sensor. And then we have our simulated robot, which is this little car thing. These blue lines are showing the range of a laser rangefinder LiDAR sensor, which shoots out laser rays and returns the distance at which the laser rays hit an obstacle. There's 360 laser rays, so for every degree around this robot, it can see the range to the nearest object in this particular plane. We can see that this is a plane. So for example, these fire hydrants have these ridges at the bottom, and this robot, because it's a LiDAR sensor, is at a specific height, which is above the fire hydrant ridges. It can't see those ridges, so it's going to have to leave a little bit more buffer space around the fire hydrant than it would if it knew exactly the shape of the obstacles. Now, simulation is valuable even when we could have the robot. I showed that Ranger robot earlier, and we could conceptually just develop robot programs directly on the Ranger. But even with a physical robot, even with a relatively inexpensive physical robot, we don't want to deal with like writing a control program, testing it, and having some bug cause uncontrolled acceleration that will make the robot break. The danger of breaking the robot and hurting someone or costing a lot of money is really obvious actually with spacecraft. In Kerbal Space Program, the first thing that happens when you start playing around is that your rocket's going to blow up because it's full of explosive rocket fuel, and you can easily imagine that every single rocket you're launching is $1 million of hardware or $100 million of hardware. But we still don't want to break our $100 robots. We don't want to spend another $100, especially since we don't have national scale budgets as either college students or college instructors. So we're going to use a simulator even for boring robots. And in a simulator we get to have some fun stuff like this LiDAR, which is a great sensor, although I can't have you buy yourselves LiDARs as a requirement for the course, because the cheapest good LiDAR, the sensor itself, is $100. That's way down from what it used to be when I was in college, when a cheap LiDAR cost $5,000. Okay, so we're simulating wheeled robots here in Gazebo this semester. At the moment, we don't have a good simulation of the Ranger. That's something that I'm going to have the TAs try to solve, get us a Ranger simulation for some of the later assignments, so that then you can move your Ranger control programs over to the physical robot if you decide that you want that for either playing around or as the basis for your final project. Gazebo is, unlike Kerbal Space Program, which really is just a game, and we're using it as a simulator just for sort of an example problem domain, Gazebo really is used as a simulator, especially in colleges, but also to some extent in industry, because it's, as an open source simulator, very flexible, and you don't have to mess with sort of licensing complications. If you develop something in Gazebo, both the simulation that you've developed and all of the resulting code is something that isn't constrained by that sort of licensing issue. So in spite of the fact that Gazebo can be a little bit annoying to set up and requires Linux and everything, it is a sort of very practical tool. Let's see. Gazebo is normally used with the ROS software stack. ROS stands for Robot Operating System, and it's this set of software, its own package manager that you install on top of an Ubuntu system. It is great for sort of serious robotics research, but it absolutely requires a dedicated machine to do anything. You have to install an instance of Ubuntu to be a ROS instance, because it kind of takes over the system. To avoid some of the complications with ROS, both in installation and in just using it, because it's a moderately complicated system, we're going to be using just the Gazebo simulator by itself, which isn't sort of the most common situation to be in, but it's something that can be done and is a useful setup, and is simple compared to the way ROS works. All right, so homework 1, let's go ahead and find a web browser and take a look at that. Firefox. Here's a web browser. So homework 1 says, let me do that. Homework 1 says that we need to set up, install Linux. As I said, Gazebo really expects that you're running Linux, and not just Linux in simulation or some compatibility mode like the Windows services for Linux that Microsoft has been releasing recently, but it actually expects that you have Linux installed directly on a physical computer. It needs 3D acceleration and some other stuff that most of the sort of compatibility modes or virtual machines or simulations don't work that well with. So for homework 1, you're expected to install either Ubuntu 20.04, which is the official supported thing for Gazebo, or Debian 10, which is what I'm running it on here, on your machine. You can try to get away with some other configuration. Other Linux distributions will probably work fine, but if you run into trouble, the core staff is going to expect you to go ahead and set up the supported configuration. With robotics, we're getting to the point where you're using sort of specialized both hardware and software, to the point that having a particular operating system on your machine to be able to use some of the tools is something that just happens. That's our requirement. Once you have a Linux distribution set up, go ahead and install Gazebo. You can get it from the website here. There's a script that you run that will go ahead and set up a package repository for Ubuntu or Debian and install the appropriate packages. Once you have the prerequisites installed, the major prerequisites, you can go ahead and fork the GitHub repository where I have the starter code for homework 1, go ahead and clone it locally, and I may use this same repository for multiple Gazebo homeworks. So if this is far enough in the future that I'll post another assignment and that messes with things, you might want to use the homework 1 branch. I'll try not to mess with things too much, but there may end up being extra stuff in here later. Once you've got the Git repository, go ahead and install some extra prerequisites to let it build. And once you do that, we can go ahead and let me grab a terminal window here. Bonk, bonk. There. Terminal windows all day long. Like that. So if we go look at the code, here's what you'll get when you clone the Git repository. You're going to get a file called sim.sh, which is the thing that you run in order to start the Gazebo simulation we were looking at, and you have this make file. And this make file is going to make it so that if you run make, it's going to build all of the code in here. That code includes an example control program, a very simple example control program that lets you sort of remote control the robot with like move forward or turn. And it includes a Gazebo plugin that actually controls the robot chassis to translate the control commands that we're sending from the control program into sort of things that make sense in the Gazebo physics engine. So the plugin needs to be built. The plugin lives in the the plugins directory here. The plugin needs to be built before you can run the sim script and expect things to work. And then the starter control program here is in Brain. You can see that also got built by the top level makefile. So once you've run the simulation, you can run this Brain thing, and the robot will do something that doesn't happen to solve homework 1. So once you've got this running, go ahead and start up your simulation. Do I have Gazebo up? I didn't finish Gazebo. Let me start the simulation. I'll start the simulation with /sim. That's going to pop up this Gazebo window. The important thing here is that we have a hello from control plugin printout. That indicates that the control plugin is actually working. If you don't see all this output, then you probably didn't successfully build the control plugin, and you're going to have to debug why. Then you have this this Brain program, which is the sample control program that you're going to want to edit into a control program that solves the task. Now, the task that you're supposed to do is move the robot from the start point, which is a x-coordinate of -20. The x-axis shows up here as red, and a y-coordinate of 0, over to the checkerboard pattern here, which is an x-coordinate of +20 and a y-coordinate still of 0. And there's some things in the way. If you bump into them, it won't work. Let's go ahead and take a quick look at the starter code that you get. You get sort of 2 C++ modules. That's what we happen to be using here, because that's the easiest thing to interface with Gazebo. There's also a Python library. If you want to port this to Python and then work there, that's fine for this assignment. But we're divided into 2 pieces. Brain.cc here is our main control program. It consists of a main function that's going to instantiate a robot object. And in the process of instantiating this robot object, we give it a callback. And every time the sensors are updated on the robot, this callback function is going to get called. And there's some logic in here that is actually just straight up wrong in a whole bunch of ways that's going to try to control the robot. But this piece is correct. If you do get to the goal, it's going to print out "we win" and then exit. But you'll have to edit that control program quite a bit to get it to solve the task. The other thing that you get is this robot module, C++ module, so it has a header file and a source file. If we look at the header file, you can see in here we have a laser hit class. A laser hit is just a value object, so an individual ray of the laser is going to be represented as a range to the object, and then the angle from the robot to that object in, I think it's relative coordinates. It should be relative coordinates to the robot itself. So as the robot turns, that angle is going to change, and I think forward is 0, but depending on the coordinate system, due right might be 0. Due right is traditionally 0 in a sort of physics reference frame. This is the sort of thing where there isn't really documentation, and you're going to have to explore what's actually going on. You can do things like moving the robot around while printing out the laser hits. Move the robot around so that the only laser hit is a particular object. All right, so now the only laser hit we're getting is this this one. The only laser hit we're getting is this one fire hydrant, and so that's sufficient for you to then be able to figure out what the angle is to that fire hydrant, and then determine what the thing is. That's something that we're going to have to do a lot in this class, and it's something that you have to do a lot in robotics in general, is figure out what the actual behavior of something is. Documentation isn't always perfect, and even when documentation is trying to be perfect, it's sometimes just straight up wrong. All right, so those laser hits are important for the LiDAR sensor. But the more relevant thing is this robot class. So a robot has some sensor state. It has an array of laser hits. There's going to be 360 of those in there, saying all the laser hits from the last laser scan. And the other thing that we have on this robot is a magical pose sensor that tells it the XY coordinates in the simulation, as well as the angle that the robot's at in the simulation in 2 dimensions. That's not something that we can really have on a real robot, but it's convenient for this particular assignment. So that is the sort of externally visible state of the robot. There's also some internal implementation. We also have an API where we can make the robot use its actuators to set its velocity, spinning the wheels forward, and set its turn angle, which is in sort of vaguely unspecified units. You'll have to play with it to see how that works. But back here we can see every time any of those sensors change, the callback gets called with the robot, and we're expected to go ahead and look at the position X, Y, and T fields, as well as the hits vector in order to figure out what the sensors are, and then we use that to figure out what we're going to do for the actuators, how we're going to set the velocity, and how we're going to set that turn value. Okay, once we have modified this control program to complete the assignment as intended, what we need to do is we need to go look at the assignment. And so we're going to write our control program. We're going to push our solution back to the GitHub repo. We're going to make sure that our control program is actually a copy of that starter code, that brain directory. We want a copy of it with your name in the directory, so that if the TAs are downloading and unpacking your code, if they unpack it in the same directory as someone else's solution, they can tell whose is whose just by the directory name. Then what you need to do is you need to create a demo video. And the demo video or solution video is going to show your program running, successfully doing what you say it's going to do. So I've solved this, and the last video for today is going to be my demo video or solution video for homework 1. They get to see my code running and doing a awful looking job that does eventually manage to drive the robot to the goal. Once you've created that demo video, you need to post it to a public video hosting site like YouTube. Then you need to write a readme hw01.md file. It should be in Markdown. If you just make it plain text, that's valid Markdown generally. And fill in your name, the URL to your Git repository and the demo video, and any extra comments. Then you want to create a tar archive of that directory you created up here. And that tar archive is what you're going to submit. I'm going to go ahead and go through and do that. So let's go to my solution. My solution here. So I'll copy my solution over to ntuck homework 1. So now I have this ntuck homework 1 directory. I'll create a tar archive. ntuck homework1.tar.gz of the ntuck homework 1 directory. Oh, we tarred it up, but there was a bunch of junk in here, like CMake files. So the result of that is that this thing is now like 400K. That's super big. There's no reason to be submitting that much junk. So I'm going to go ahead into ntuck homework 1 and type make clean. That'll remove the build directory, which will make it quite a bit smaller. So now if I tar this up, it's a 4K file that I'm now going to submit here. To do that, I'm going to poke new submission. Oh, I need to make that README file. All right, README homework1.md. 3 things. Name, nat tuck. URL, git repo. then video is going to be some YouTube URL that wants to actually be a video that the TAs can go ahead and check out and see your code working. And then I don't have any comments, so that's fine. So now that I've done that, we can go ahead and tar that up. Then we're going to say new submission. I'm going to browse for my solution. We can then submit and upload it. And then a very important step when you upload homework to Inkfish is that you want to hit the View Files button. I'll make sure that you uploaded the correct thing. We can see here that I uploaded a directory as instructed. We have a README homework 1. We can actually see the content. This is what the TAs are going to be grading. We can see my source code. The TAs have comments on your code. They'll put it in here when they grade it. And that is how we submit a file to Inkfish. Alright, I think that's the whole story on this. So the next video after this is going to be my video for my my homework 1 solution. And good luck on homework 1. I will see you, you're probably watching this after the first class, so I'll see some of you next class, and next week there'll be more videos.